Hi there. Welcome to this lecture series on matrix algebra. This is lecture 16, part 2. In part 1, we covered some basics on least square approximations. And today we'll continue our discussion. Let's get started. Now we consider least square interpolation. So, consider the following situation. We have a function f, and it depends on n unknown coefficients c1, c2, and cn. And f is a linear combination of functions f1, f2, and fn in this way as written here. So, for example, f of x could be a polynomial c1 plus c2x, so where f1 would be 1, f2 will be x, or a second degree polynomial, so c1 plus c2x plus c3x squared. And there are other possibilities. For example, it could be a trigonometric function, so fx could be a linear combination of sine x, cosine x, sine 2x, and cosine 2x. Okay, so in this case, then we'll have 4 coefficients, C1, C2, C3, C4. Then to determine these coefficients, the C's, we make several measurements. And this will give us a set of data points. Let's say we made m points. So I have data points, x1, y1, that's 1 point. So x2, y2 is another point, and then all the way to xm, ym. In the ideal situation, these data points should lie on the graph of f. So what does that mean is that we would like to have that if you evaluate the function f at the point xi, you should get the value yi. And this should be true for all the points I from 1 to 3 all the way to m. And then we can write these out into m linear equations and put it in the expression for the function f using the coefficients. Okay, so for first example, f of x1 equal y1, and put x1 in f, we'll get c1 f1 at x1, c2 f2 at x2, plus all the way to cn fn at x1. That should equal to y1. Okay, and then the function evaluated at x2 should be y2, and so on and so forth. You go through all of them until the last one. The function evaluated at xm should equal to ym. So we see that we have m linear equations and we have n coefficients. And we can write it in the matrix notation, and considering the coefficients c's as the unknown and all the function value at the xi's for the function f1, f2, fn will be the coefficients. So that will be the A matrix, and that's the C, the unknown vector, and then we put the y case in the vector y. Now, in most applications, we would have measured at many more points than the number of the coefficients. So the number of equations m is much bigger than n, the number of the coefficients for the function f. Okay, and this system has no solution. There are so many equations with so few unknowns. So, however, we can try to find a approximation that minimizes some distance. So let's define the distance to be the square of the norm of the residual. So AC minus y squared, which is the this is a vector, so each element of the vector, the ith one, take this form, and that's square, and we sum over all of them. So we want to find the coefficients ci's such that this distance is minimized as small as possible. Okay, so instead of solving this equation AC equal y, which we know we don't have a solution for that, now we can solve the system A transpose A times C equal A transpose times y. Okay, so this step here is the derivation we did in the first part of the lecture. Okay, so let's take an example. So we have an unknown function f. It has been measured at 4 points, x1, x2, x3, x4. They are x1 is at -1 and the function is 0, so that's your y1. And at x2, which is 0, the function y is 2. And then at x3, 1, the function is 3. And then at x4 is 2, the function equals 5. So here we plot it. These are the measurements, the red dots. And now we want to find a function f such that f at xi shall be y, and that is the f evaluated at -1 shall be 0. That's the first data point. And the second one, f evaluated at 0, shall be 2, the second data point. And the third data point is f1 is 3, and the fourth data point is f2 is 5. Okay, so assuming the function f is a straight line, here in the graph here we plotted a suggestion, kind of a possible looking function. F of x is c1 plus c2 times x, and we need to find the coefficients c1 and c2. So such a process of fitting in a straight line into a set of data is called a linear regression. Okay, so that's the data set, the requirement, and then let's discuss linear regression. So here we assume that fx is c1 plus c2x, and c1, c2 are two coefficients. This is a polynomial of degree 1, and the graph will be a straight line. And we want to determine the coefficients c1, c2 such that the function f here will best fit the data, and best fit in the sense of least square. Okay, let's be patient and write out the details of the problem that we will formulate. Okay, so now we set the two functions here. Call it first is f1, which is constant 1, and then the second function is x. We call it f2 of x is x, and we now seek two coefficients c1, c2 such that this linear combination, when fx is c1 f1 plus c2 f2, which is c1 plus c2x here, they would satisfy the following. So f at -1 is 0, f at 0 is 2, f at 1 is 3, f at 2 is 5. So it satisfies the data set, the 4 points there. And we can put in the function f1 and f2 in detail here. This will give us c1 plus c2 times x, which is -1 is 0. And then the second one is putting x to be 0, and it's 2. And the third one is put x to be 1, that's 3. And the last one is x is 4, and it's 5. Okay, so we have these 4 equations with two unknowns, c1 and c2. So we would like to solve this system of 4 equations and 2 unknowns, and it's easy to see that it does not have a solution, because if those 4 points are not in a straight line, then you cannot find a straight line that will go through all 4 points, right? So we'll do the next best thing. Okay, so to utilize the algorithm we derived for the least square method, we will now write it in matrix form. We write this as AC equal Y, and this will be the A matrix, and that's the C, the unknown, and then the Y is the vector on the right hand side. So instead of solving AC equal Y, we now solve A transpose A times C equal A transpose times Y. Okay, so that's the formula we derived. Okay, then let's put in, we transpose A put here, and that's A. This is C, and that's A transpose, and that's Y. So we can work out this matrix multiplication and this matrix and vector multiplication. After working out those products, and we have the system here. So this matrix times that give you this 2 by 2 matrix, and this matrix times that gives you a vector of length 2. And then we see that that is a symmetric matrix, and it's a 2 by 2 matrix. Using whichever your favorite way of solving it, we can solve this system of linear equation, and we can find the values for C1 and C2. Okay, there are these two numbers. Then we can plug them back in and state the result. That is now the polynomial of degree 1 that best interpolates our given data set is this function. F of x is C1, which is 17 over 10, plus C2, which is 8 over 5, x. Okay, so that's all for this lecture, and in the next lecture we will give a very brief review on complex numbers, and because that knowledge would be extremely important in future studies on this topic. Okay, so I hope you enjoyed this short video, and I'll see you next time.